for this section, 12.3, I want to talk about optimization. So I'm going to define absolute minimum and absolute maximum. Then we're going to talk about optimization and from a graphing standpoint and a calculus standpoint. And then I want to apply optimization to finance and geometry. Okay. So first thing we need to talk about is absolute minimum and absolute maximum. So the minimums and maximums of absolute and local, they work the same, except they for an absolute minimum and maximum, those occur on a closed interval. So we're only going to look at a function from maybe, from like -2 to +4. And then we can find an absolute max and min that occur on that interval for the function. All right, so then that brings us to the extreme value theorem. And the extreme value theorem basically just says that if we have a continuous function on an interval, so from like -2 to 4, then the absolute extrema will either occur at the endpoints of the interval or the critical points that are on that interval. Okay, so those are the only places that some kind of absolute extrema can occur. And again, I'm not worried about you knowing what the extreme value theorem is as far as what it's called, but just know how it works. Okay, so for an absolute max and min, we have this function that's defined from -2 to 6. So we're only going to consider from -2 over to 6 on the x-axis. Okay, it can have maxes and mins in between -2 and 6, but our absolute maximum is the largest of the maximums, and then the absolute minimum is the smallest of the minimums. And as you can see, we have this absolute minimum when x is equal to 3. And we have an absolute maximum when x is equal to 4 on the interval from -2 to 6. So let's do one ourselves here. So we're going to look at this function h of x from -4 up to 2. So I'm going to look from -4 up to x is equal to 2. Okay. All right, so at -4, I am at this point. Okay. And then I do have a potential of a minimum here because I have that valley, and then I'm increasing it all the way over to here. Okay. All right, so that means that I have an absolute max at x is equal to 2. Then I have an absolute min so the bottom of the function, so to speak, or the low point, occurs at x is equal to -2. Okay, so those would be the absolute max and mins. Even though I have potential candidates, those are the absolute because they are the largest and smallest of the maximum and minimums. All right, so now if we don't have a graph, we can do this from a calculus standpoint. So I'm going to take the derivative of this because I'm looking for critical points. So I have 3x squared minus 2x minus 1. Okay. So I can factor this, or I can use the quadratic formula. So I have -b plus or minus square root of b squared minus 4ac all over 2a. All right, so b is -2, so I have the negative of -2, so I have +2 plus or minus. I have -2 squared minus 4 times a is 3 times c is -1 all over 2 times a, which is 3. Okay. Plug this in the calculator and you get 4 minus a positive 12 now, so it's really 4 plus 12. So I have 2 plus or minus the square root of 16 divided by 6. So x is equal to 2 plus or minus 4 over 6. So x is either equal to negative 1/3 or x is equal to 1. Okay? So now I only have to consider the function at the endpoints or a critical value that's on the interval. Since my interval is 0 to 2, I only have to consider that 1 point of x is equal to 1. So I can ignore x is equal to negative 1/3. So now I want to evaluate this function at the endpoints and the critical value. Okay. So I plug this in the calculator, f of 0, and I get 10. I plug in 1, and I get 1 minus 1 is 0. Minus 1 is negative 1 plus 10 is 9. I plug in 2, I get 8. Minus 4 minus 2, that's positive 2 plus 10 is 12. So I have an absolute min at x is equal to 1, and I have an absolute max at x is equal to 12. Okay. That would be how to find the absolute min and max given a function. Okay, so now I want to apply this optimization to revenue, cost, and profit. So let's say a manufacturer produces grills that sell for $400. Then the total cost of producing this certain number of grills is approximately this represented by this cost function. So first I want to write a revenue function for the situation. Okay, so the revenue function is always equal to the price that we're selling it at, the item at, times the number of items sold. So we are selling at $400 a piece. We don't know how many items we're going to sell, so we'll just call that X. So our revenue is 400X. Okay. Our profit is always the revenue minus the cost. So my profit function is equal to 400X minus this whole cost function, $525,000 minus 30X plus 0.12x squared. Okay, I'm just going to write it up here so I just have plenty of room. All right, so then I negate everything that's in the parentheses, so I have negative 0.012x squared. I have minus a negative 30x, so plus 30x, so plus 430x, minus 525,000. Okay, so this is our profit function. Now, to find see what number of grills should we produce for maximum profit, I could take the derivative of that profit function, set it equal to 0, and then see if that is the maximum. Or I could look at this from a graphing standpoint, and I could graph that profit function. So let's graph the profit function. So then I go up to the top of all this, and I see that I have a maximum when x is equal to 17,900, and since we're talking about grills, we'll round it, 17,917. Okay, So 17,917 would be the number of grills that I would sell for a maximum profit. All right. Now I want to figure out what the maximum profit is. Well, I graph the profit function. So my maximum profit is represented by the Y value, which is $3,327,083. Okay, so that is the maximum profit. So I could have found that out by taking the derivative of the profit function, setting it equal to 0, and so on, or I can graph the profit function and just see that the maximum happens at that value. Okay, let's look at another example. This time we're going to use geometry. Okay, so we have a fence that's being built that encloses a rectangular area of 5,000 square feet. And so optimization means that we're going to maximize or minimize. So here we're trying to minimize. All right. So we have this cost of fencing for the north and south sides. We'll say $1, and in east-west we'll say $2. Okay. So let's find the cost of the least expensive fence. So our fence is going to look something like this. All right. It's going to look like a rectangle. And we'll say that the short side, we'll say X and Y. It really doesn't matter, but that's what we'll say. Okay. Well, the perimeter is equal to, we're going to need to account for 2 of the X values plus 2 of the Y values. Well, my cost function, or my cost equation, is we'll say the X sides times $1, because that's how much it costs for the X sides, and then $2 on the long side. So we need to multiply. All right, so that becomes 2X plus 4Y. So that is my new cost equation. Okay, I'm trying to minimize or maximize here. Here I'm trying to minimize. So I would normally take the derivative. Well, I do not know how to take the derivative of something with X's and Y's. Okay. So we need to do a little side work here. Well, the area needs to be 5,000 square feet, and area is equal to X times Y. Okay, so I need to make sure that when I multiply my X and Y together, that I get 5,000. Okay, because I have to enclose a certain area. All right, so I'm going to rewrite this area equation by dividing by X to get Y by itself. So my new area equation is 5,000 divided by X. Now I have a Y here, I have a Y over here in my cost equation, so I can substitute that in. So 5,000 divided by X, substitute it in. All right. Now at this point, I could take the derivative, set it equal to 0, solve for X, all that good stuff. Or I could look at it from a graphing standpoint. So let's look at it from a graphing standpoint. We graph this cost equation. All right. I do get another potential value down here, which is that X is equal to negative 100. However, thinking about my interval, right, I can't have a negative length of a fence. So I do not even need to concern myself with this. So what I am looking at here is I have an X value that is equal to 100. Okay, so I know that I need to have 100 foot of fence on the X side of the rectangle. Okay, so X is equal to 100. Now I have a place where I can substitute X back into to find my Y. So remember, Y is equal to 5,000 divided by X, which is 100. So Y is equal to 50. So now this X and Y would give me my minimum cost with my least expensive fence. So I can substitute those back in to my X and Y's. So I have 2 times 100 in my cost equation plus 4 times 50. And that is equal to 200 plus 200 is 400. So I could put this fence in for $400 to enclose that area by allowing the X sides to be $100, or excuse me, 100 feet, and the Y side to be 50 feet. Okay, and my cost for that would be 400. I can also see that at the point 100 and 400, but I do not know what my Y value would be to make that true. So you would have to solve that if like I did. All right. So that is all for 12.3. If you have any questions, feel free to email me. If not, have a great rest of your day.